Hello, everyone. Welcome to this new seminar of the Nagrams series. The speaker of today is Tommaso Taddei from INRIA team Memphis. And we are very pleased to have him in this seminar series. And today he will discuss on his recent work about one-shot domain decomposition methods for component-based model order reduction. Tommaso, please go ahead.
Thank you very much, Francesco, for the nice introduction, and thanks Trajan, Virgul, and Maria for inviting me to this seminar series. So I'm going to present today some work on component-based model reduction, and this work is in collaboration with a former PhD student, that Giulia Sambataro, that just finished her PhD thesis, I guess, 3 months ago, and Angelo Iollo at INRIA, and also Katrin Smetana now at Stevens Institute in the US. So this talk is about parameterized model order reduction, PMOR. And as I'm sure everybody here knows, the goal of PMOR is to reduce the marginal cost associated with the solution to parameterized problems, where marginal means in the limit of many queries. Model reduction is motivated by real-time and many query problems that naturally arise in design optimization, uncertainty quantification, optimal control. Just to fix notation, we consider problems of this type. So we seek a solution U of mu in some Hilbert space curly X that satisfies this variational equation for all test function V in a suitable test space curly Y, where mu here is a vector of parameters that might represent material properties, geometric features, and so on. Curly M here denotes the solution manifold, which is the collection of the solution to this PDE for all values of the parameter in a prescribed parameter range. So I want to start with something very basic, which is the general recipe of model order reduction, and I will clarify later on why I call it monolithic. So the general idea of model reduction is the following. We seek approximations of this type, where Z is in general a linear map from Rn to an Hilbert space curly X, and alpha et is a vector of generalized coordinates that depend on the parameter. The idea of model reduction is to decompose computations in 2 phases. During the offline phase, we estimate the solution to this problem for several values of the parameter using an high-fidelity solver, say a finite element, a finite volume solver. Once you've done that, we exploit this information to build the reduced ordered basis big Z and what we call the reduced space curly Z. And then we define a reduced ordered model for the generalized coordinates. Then, during the online stage, given a new value of the parameter, say mu prime, we solve the reduced ordered model to estimate the solution coefficients for that particular value of the parameter. Finally, we estimate the error between our estimate and ideally the true state. Okay? So what I would like to emphasize here is that those approaches rely on 2 fundamental assumptions. Assumption 1, the solution is defined over a parameter-independent domain, or possibly over a family of diffeomorphic domains. And you can see this in the fact that this space is parameter-independent. Okay? It is relatively easy to deal with the family of diffeomorphic domains. Essentially, we apply some geometric transformation to remap the problem over a parameter-independent configuration. But in general, we cannot deal with topology changes. To provide an example, consider the situation in which the parameter is the number of columns in this structure, and we have 2 different structures like that. We cannot expect to find a diffeomorphism that maps these 2 configurations into a single configuration. Okay. Second assumption, it is possible to solve the full ordered model for several parameters during the offline stage. Of course, this is another major assumption because there are certain classes of problems for which the actual goal of model reduction may be to reduce, maybe it would be simply unfeasible to solve the problem for just one configuration. These two observations have motivated a lot of research that goes, let's say, under the name of component-based model reduction. The idea is pretty simple. So during the offline stage, we define a library of archetype components. For instance, a library of just one component, which is a parameterized T-junction, like that. Okay. Then we build local reduced ordered bases and local reduced ordered models for each archetype component. During the online stage, we define a system as instantiation of these components, okay? In this example, we interpret this system as instantiation of 3 T-junctions. Then we solve the global problem by suitably gluing together the local reduced order models. So that's the idea. So effective implementations of component-based model reduction requires to address 2 major issues. The first question is, how can you glue together local reduced order models to estimate the global solution? If you think about this, is the question of domain decomposition in a sense. And the obvious desiderata are quasi-optimality, meaning we would like estimates that are as close as possible to the best fit error. And also, we hope that the implementation is not going to be too tough. Okay, so let's say we hope for simple implementation. The second question is, how can we build good approximation spaces for each archetype component? And here, let's say the requirement is that we would like local solves, meaning that we would not want to rely on global solves in order to build these local approximation spaces. And also, we would like fast converging approximations, in general, faster than polynomial type general approximations like finite element. So my work here at INRIA is to try to develop an effective component-based model reduction paradigm for nonlinear PDEs. Okay. So the talk is divided in 2 parts. In the first part, I will talk about, let's say, a possible answer to the first question. So it will be about domain decomposition, and we'll present an approach which is essentially based on an interface control variable and on a formulation which reads as a nonlinear least square problem, which is solved using the Gauss-Newton method. The second part of the talk will be about data compression and covers a recent paper that I have done together with Dr. Catherine Smetana from Stevens Institute. Okay, so let's start with part 1. So I want to start with a very standard domain decomposition method, which is the overlapping Schwarz. So I will consider the case in which you have just 2 components, but it doesn't really matter. So we consider this problem, written again in variational form, in the domain omega. And we consider the following overlapping partition of omega, omega 1 and omega 2, with interfaces gamma 1 and gamma 2. Okay. I introduce the spaces xi, so the restriction of the elements of x to the domain omega I, and xi0, which is the bubble space, so the function of xi's that vanish on the port. Then we can rewrite the standard overlapping Schwarz method in this way. So we prescribe the solution on the port gamma 1, which is inside omega 2. We solve the problem in omega 1. Now we have the datum on gamma 2. And we solve the problem in omega 2 by prescribing the datum on gamma 2. Okay? And then we iterate. Not that here we consider a multiplicative overlapping Schwarz method, but we could have also considered the additive version of it. So If successful, any limit state of the overlapping Schwarz iterations must be equal to, so must satisfy this condition, meaning that U1 star, so the solution on the left-hand side, should be equal to the solution on the right-hand side, okay? On these two ports, okay? What that means is that this limit state minimizes this objective function subject to the constraint that the PDE is solved individually in each subdomain, okay? So if now we look at this, we start with, say, with this formulation, we call it this one-shot overlapping Schwarz method, OS2. And we would like, instead of considering the overlapping Schwarz, we would like directly to consider the minimization problem, which is, in a say, solved by the same limit state as the limit of the overlapping Schwarz. The obvious questions that we would like to address are try to understand the structure of this optimization problem and try to come up with possible effective solution strategies to solve it in the presence of model reduction. So in order to achieve this goal, we first introduce a field solution decomposition. So again, a little bit of notation, we introduce what we call the port space, which is the restriction of the solution to the ports, and the bubble space of solution in Xi that vanish on ports. And we introduce what we call an extension operator, EI, from the port space to the let's say, local space Xi, which is defined in this way. Think about this as a standard harmonic extension, for instance, okay? Then we can see that any field in Xi can be written in this way. So it's a bubble component plus a port component, okay? Which is associated with the particular extension operator that we consider. So now we can introduce what we call a port to bubble map. So given an element on the port space, we define Fi of W as the solution to this problem, okay? This means that the local solution to the original problem that we consider, which I denote by UI, is uniquely determined by the port solution, so UI restricted to the port, and can be written in this way, okay? Where this is the bubble component and this is the port component. So in the language of control, we can interpret this port as a control variable in our problem, in our formulation, okay? So let's now introduce a discretization of our problem. And for this, for the sake of argument, we does not distinguish between high fidelity and low fidelity reduced order discretization. So we just introduce bubble and port basis, okay? And we consider the following ansatz. Then we can rewrite the objective function U1 at minus U2 at in this way. P and Q here are linear operators, since essentially we consider a linear reduced order basis, and this is a let's say a quadratic objective function. Then we introduce Galerkin, local Galerkin models, defined in this way. And then we introduce the algebraic port to bubble maps from Rm, so from the space of port coefficients, to Rn, the space of bubble coefficients, which satisfies this equation. So it's defined implicitly by the Galerkin model of each subcomponent. Okay. So by introducing this field decomposition, we rewrote the one-shot overlapping Schwarz statement as a non-linear least square problem of this form. Okay. Where F is the union of all port to bubble maps. Okay. Note that since Fi of beta I satisfies this equation, the gradient of F is block diagonal and satisfies this formula.
Excuse me, Tommaso.
Yeah.
Can I ask you, what do you mean? But where's the one-shot part in this? You speak about one-shot.
Oh yeah. So that's just a name, but the name is that compared to, let's say, if you do overlapping svars for a linear problem, you would still have to iterate.
Of course.
While here we don't iterate if the problem is linear.
But you are solving the minimization.
Yeah, and so that you can use a linear, let's say an iterative method to do so. But it's in the same spirit as one-shot methods for, say, control problems.
Okay, thanks.
So that was kind of the analogy. But let's say the rigorous answer is, if the problem is linear, you don't iterate. While with svars, you iterate even if the problem is linear.
Okay.
Thanks for the question. Oh, feel free to stop me anyway. So what I wanted to say by this statement is that given n, meaning the number of bubble modes, and m, the number of port modes, the evaluation of these local port-to-bubble maps requires to solve a nonlinear, in general, nonlinear problem of size n, while the evaluation of the gradient of Fi requires to solve m linear systems of size n. Okay. So let's now try to identify 3 different strategies to solve this problem. And with no surprise, one strategy is the standard overlapping svars method. Okay. So we started with overlapping svars. It's not a surprise that the overlapping svars is one particular way of solving this problem. Another class of methods relies on steepened descent quasi-Newton methods. Those methods involve the evaluation of the gradient of the objective function. Okay. And so we need to compute the gradient of f in order to, compute this gradient of g. However, exploiting the structure of the gradient of f, the computation of grad g involves the solution to just 2 linear systems. And this is because we don't need to assemble really the gradient of Fi, but we just need to compute one linear system associated with this inverse. Okay. The third class of methods are Gauss-Newton type methods. For convenience, I just consider the Gauss-Newton one. And you see here that those methods require the full assembly of the gradient of f, and also require a solution to a least square problem of size m equal to NDD, meaning number of subdomains, times lowercase m, which is the number of port modes in each subdomain. So let me make a few comments here. So the Gauss-Newton method exploits the structure of the minimization problem. Okay, it's the only one that really exploits the fact that the problem is a non-linearly square problem. And so it's expected to be more robust and converge in fewer iterations. Of course, this is, let's say, is a guess, and it needs to be confirmed by numerical experiments. Another observation is that the cost per iteration of the Gauss-Newton method is expected to be much higher than the other methods. Because, as I mentioned here, we need to assemble the gradient of f, as opposed to the other 2 methods. Okay. So the message I would like to convey is that the Gauss-Newton method is computationally feasible only if the number of port modes is moderate, because this gradient scales with the number m of port modes that we have. Note that here we can allow ourselves to consider local full-ordered models. So we can consider models in which n, the number of bubble modes, is large. On the other hand, m should be small for all components. The other message is that the Gauss-Newton method can be of interest if the dominant cost is associated with the solution to local problems. I would also like to do, let's say, a more like numerical analysis type of slide, just one really in this talk. And I would like to do a different derivation of this overlapping OS2 statement. So we introduced the tensor product spaces x0 and u in this way. We introduced the linear operators associated with the matrices P and Q that I introduced before. And I introduced the infinite dimensional port to bubble operator. Okay. Then you see that the port solution satisfies this operator type equation, which is defined only on the port, so on gamma 1 and gamma 2, the union of gamma 1 and gamma 2 in our example. So if you exploit this notation, you can see that the OS2 formulation is based on the following consecutive approximations. Approximation 1, we perform a minimal residual approximation of this equation, okay? By considering the minimum in L2 of over a suitable test of set of functions, okay? The port functions. Approximation 2, instead of computing the exact port solution, we consider a local an approximation of the port to bubble map, okay? And this is related to the accuracy of, let's say, the bubble part of our approximation. The third approximation is associated with hyperreduction. So I haven't talked about that. This is quite technical for those of you that are not doing that all the time. But essentially means that instead of computing this integral over the entire domain, so over the entire port, we can compute over a select number of points, okay? So why I think this, let's say, derivation is relevant? First of all, this is the starting point of the analysis for cursive problems. That is what you've done in the paper. In perspective, on the other hand, I think this is quite interesting because it can also help us devise minimal requirements for these port-to-bubble maps. And I will come back later on this point. So let me now present some numerical results. I here consider the results for a nonlinear steady state problem, but in the thesis of Julia, there are also results for an unsteady THM problem, if you want to check out. So this is the problem that we consider. So this is a Neo-Hookean material law. We consider, let's say, different source terms in terms of a stress term on these boundaries in red. I hope that you can see. And basically, we have 4, let's say, global parameters. The Young modulus in 3 subregions. And the intensity of the source term on those blocks. Plus, we have a, let's say, a topology type, topology varying type parameter, which is the number of those source terms. And you can see that if we change QA, so if you change the number of repositories on the bottom side here, these induce a topology change, so we cannot directly use standard monolithic model reduction techniques. In this test case, we don't do any localized training, so we rely on global parameters and global solves to perform, let's say, to be the local approximation spaces. Okay. So a bit of details. Computation are based on a P2 finite element discretization. Okay, but that's quite standard. We rely on a Galerkin projection of the local problems and on mesh sampling and weighting hyperreduction to devise the reduced order one-shot statement. You can see all the references if you want. I can also provide more details on that. Also, we assess performance based on this out-of-sample average prediction error, which is defined in this way. Again, a little bit of technicalities here. Since we have overlapping decomposition, we would like to compute the error in H1 over the domain omega. And since these guys had overlap, one way of defining a single field everywhere in omega is through a partition of unity operator. Okay? Exactly like in PUFM type of methods. So first result, I show results for the 3 optimization methods, Gauss-Newton, Quasi-Newton, and overlapping Schwarz. And this is the average objective function as a function of the number of port modes that we have. Number of bubble modes is taken the same. And what you can see here is that all the 3 methods perform quite similar in terms of the value of the objective function. And this is not a surprise. We all trying to solve the same problem, okay? The observation on the other hand is that the number of iterations changes quite dramatically for the three approaches. It's around 3 here, it's around 100 for overlapping Schwarz and quasi-Newton, okay? I think it's also interesting to assess the sensitivity of those methods with respect to the size of the overlap. We all know that if the overlapping size goes to 0, so delta goes to 0, those methods don't converge. But we would like to see how well they perform when delta is small, okay? LQ here is the size of one repository, and so we measure delta with respect to the size of one repository, okay? So here you can see the results in terms of objective function. What you can see here is that, again, overlapping Schwarz and Gauss-Newton provide pretty much the same, have pretty much the same performance in terms of objective function for the different values of delta. But when you look at the number of iterations, we see that the number of iterations is still pretty dramatically different. Here is pretty much always equal to 3. And here, on the other hand, depends quite significantly on the value of delta. So it's around 50 for delta equal to 2/3 LQ, and it's around 100 for delta equal to 1/6, so 4 times smaller. Okay. While here it seems significantly more robust to the choice of delta.
And they cost from the CPU time.
Oh, yeah, next slide. So one comment on that. This is a all serial implementation, but we can assume that the quality of the code is homogeneous, or at least that's the assumption here. And this is the wall clock time with respect to the number of modes. And you see that even if the cost per iteration of Gauss-Newton is significantly larger, we still gain a factor of 20, more or less. And of course, this factor depends also on the size of the overlap. If the overlapping size is smaller, the gain is higher because overlapping Schwarz requires more iterations. Okay. So that's the first part of the talk. What I would like to do now is to talk about a little bit about localized training. Okay, and this is a work together with Katra Smetana. I will consider a different test case. So this is a nonlinear diffusion problem. Basically, this is the expression for the diffusion coefficient, which is nonlinear. We have 2 parameters in each subregion, omega I, and we have an additional parameter which is associated with the source term. Okay. So this is an idealized model for subsurface flows. What I would like to emphasize here is that this is quite challenging for monolithic model reduction because we have a lot of parameters. And also, if we allow ourselves to change the number of subdomains, then we end up with a topology change, so we cannot deal with it really with standard monolithic techniques. This is just to give you a sense of how the solution looks like. So here we have 100 components, 10 by 10. And these are 3 snapshots for different values of the parameters. So how to apply model reduction to this test case? So we introduced 3 archetype components: corner, edge, and internal components, which are associated with 3 different reference domains, which actually in this test case are the same. We introduce a label for each instantiated component. So each instantiated component can be either corner, edge, or internal. And we introduce a mapping from the reference component to the instantiated component. Again, as in the previous test case, we consider an overlapping domain decomposition technique. So those guys are overlapping. Okay. So we can now clarify what we would like to approximate. So we want to find approximation space at Z corner, Z edge, and Z internal for these localized manifolds. Note that these manifolds are defined over a, let's say, a local domain, omega F dot. dot equal corner, edge, or internal. However, in order to compute elements of these manifolds, we need to solve a global problem, because the elements of these manifolds are restriction of the global solution to one particular domain of type dot mapped in the reference domain. Okay. And so the task here is to find local approximation, so low dimensional approximation of these manifolds, but we don't want global solves. Okay. So the key idea here is that basically those elements of these manifolds solve the PDE of interest for select parameter values and for select boundary conditions on the boundary of omega at. Okay. So in a sense, we trade for global parametric variations for local parametric variations, so variations that happen inside the reference component, plus variation at the boundary of each component. Okay. And so we can interpret boundary conditions as additional parameters from a model reduction standpoint. Okay. So this is the fundamental idea. So as already mentioned, we want to find low dimensional spaces of this type. So the idea is that we introduce what we call a patch or omega oversampling that contains the reference domain with input boundary gamma in. We introduce a transfer operator which takes as input a local parameter value mu and the boundary condition G defined here, and returns the solution to this problem restricted to the domain of interest. Okay. And then we define the what we call the oversampling manifold in this way. Okay. Note that we don't prescribe directly the boundary conditions on the reference component, but we prescribe over a domain that is slightly larger than it. And I will come back later on this point. For those of you that are familiar with these sort of things, this is the same idea that people do in multi-scale finite element methods, and it's called oversampling. So we started with those manifolds. Those are the manifolds that are the target manifold that we want to approximate. And we now introduce these oversampling manifolds, where now we have, let's say, two types of parameters, the local parameters and the boundary condition type parameters. The advantage here is that in order to compute this guy, we don't have to solve the problem globally. Okay? It is clear that if the set of boundary condition big G is sufficiently large, then the target manifold is contained in the manifold M at, okay, in the oversampling manifold. The problem here is that the set G should be representative of the behavior of the solution. And in absence of prior information, G dot is going to be very high dimension. So, few comments here. One, oversampling techniques rely on the filtering properties of the operator, of the transfer operator P, and on the spatial separation between where we prescribe the boundary condition and omega at to ensure the existence of low rank approximation, even when G is irreducible. Think of the situation in which G is the entire H1/2 of gamma in. Even in that situation, we can prove that this manifold is compact, and so that this allows that can be approximated using a low dimensional approximation space. Okay. And then we rely on proper orthogonal decomposition to build the space, curly Z, for the oversampling manifold, based on random samples of the boundary datum and the local parameter. So here, I would like to, again, in the spirit of numerical analysis, I would like to clarify that the approach that I presented here relies on three fundamental conditions that need to be verified. One, the oversampling manifolds admit a low-rank approximation. Of course, this is highly problem-dependent. One necessary condition is the compactness of the operator. But in general, this is really, let's say, related to the decay of high-frequency modes. And so it's related really to the differential operator that we are considering. The second condition is that the accuracy of local approximations, so the fact that local approximation spaces are good, should imply accurate global reconstructions. And this is a feature of the selective domain decomposition strategy. For, let's say, partition unity method, there are some strong theoretical guarantees. For other domain decomposition techniques, also, for the particular technique that you have developed, there are strong guarantees for coercive problems. Okay. The third condition is that random sampling should provide near optimal results. Again, there's a lot of theory on that for linear problems, and those are essentially techniques related to randomized linear algebra. For nonlinear problems, this is, to my knowledge, still an open question. Okay, it's really a different problem, much tougher problem to guarantee. I would like very briefly to talk about the sampling distribution that we consider. And the message here is that the sampling distribution is quite tricky to solve, tricky to find for nonlinear PDEs. So let me explain how we chose it for the particular test case that we consider. So this is the problem, just to refresh your memory. And the first observation is that U here is a saturation coefficient. So it should be between 0 and 1. And so it makes sense to impose that the boundary datum sticks between 0 and some quantity U max. Second observation is that U of mu restricted to gamma in is expected to be at least H1 half. Okay. And so we would like to promote smooth sampling. So we would like that our samples are smooth, okay, in a Sobolev sense. So how to achieve that? So the idea is the following. So we consider expansions of this type, where these coefficients are Gaussian, independent Gaussian random variables. Okay. Then it's easy to verify that for any alpha in the natural numbers, the random variable x, which is the H alpha norm of this quantity, is distributed as a chi-square distribution with 2.5 degrees of freedom. So the message here is that the value of alpha, which is a user-defined parameter, encodes prior knowledge on the regularity of G tilde. The issue here is that this probability density function does not encode the fact that the image of G should be between 0 and U mar, and also G tilde here is complex valued. So to fix this, we simply perform the following algorithm. So we draw uniform random variables in 0 U max. We draw Gaussian random vectors. And then we define G prime as the real part of G tilde, and G tilde is defined here. And then we scale G in order to ensure that belongs to A and B. Okay. So this is how the solution looks. So our G looks like. So again, this is for the internal component before the rescaling. So this is with alpha equal to 1. This is alpha equal to 2, and this is alpha equal to 3. Okay. So as you see, this parameter alpha can be used to, let's say, regulate the smoothness of the boundary datum that we prescribe. In terms of actual programming, we perform randomized training. So basically, we prescribe the number of training points. If you want, also the number of test points and the number of n that tells the size of the reduced basis that we seek. We draw random parameters, mu and g, mu, this local parameter, and G is the boundary condition. We solve the transfer operator problem, and then we perform a POD. And if you wish, we can use out-of-sample configuration to test the performance of our approximation to see if you have to consider additional parameters or not, additional samples or not to perform a POD. Okay. But again, this measure is related to the particular sampling distribution that we consider, okay, which is user-defined. So let me now present some numerical results for the test case that we consider. So first of all, we perform localized training based on 200 simulations for each component. And these are the oversampling domains that we consider, okay? One additional parameter that we have to set, basically, I said before that we have one source term, but we have to describe the case in which the source term is inside the particular oversampling domain that we're considering, or is outside. And here we assume that the source term is activated with probability equal to 0.5. Okay. In terms of performance, we compute n-test global solutions for NDD equal to 100 subdomains, and we extract the solution in each element. Okay. And then we use these data sets of local solution to measure performance of localized training. Again, you can see that this particular procedure induces let's say, a local sampling distribution, okay? Which is, by the way, is not the same distribution that we used to train our local reducer model. The reason is that let's say, the global sampling distribution is largely unknown in practice, and we cannot expect to know it, okay? Let me now present the error measure. So we consider the average H1 relative projection error at component level, and we compare performance of smooth sampling for various values of alpha, Gaussian sampling with clipping, meaning that each Lagrangian node on the port is treated as an independent Gaussian random variable and is clipped so that it's going to stay between 0 and umax. And then a POD space based on 30 global sols. So what you can see is that basically this one is not really computable for practical application because this relies on global sols, but is important as benchmark, okay? And here's the performance. So what you can see in this plot for different values of n, and this is the out-of-sample prediction error, is that Gaussian sampling is quite inaccurate for edge and corner components. So if there's one take-home message for this second part of the talk, is that for nonlinear PDEs, sampling does matter a lot, okay? So it's very important to sample correctly. I also wanted to present one slide on the global projection, on the global error. And what you can see here is that if you use partition of unity, we obtain essentially near optimal, essentially optimal performance. So for this particular test case. And we haven't done for the OS2 formulation, but we expect pretty similar results also for OS2 for this particular problem. So as last slide, what I would like to say is something about model in perspective. So what you can see is that the choice of the sampling distribution is challenging and matters a lot, okay? In this particular sampling distribution that we considered, okay, has several hyperparameters that need to be carefully chosen. Of course, we believe that this was a good choice, and we believe that we also did some sensitivity analysis for the smooth sampling technique. But still, this is user-defined and is highly problem-dependent, okay? On the other hand, the sampling of global configuration is supposed to be significantly easier. For instance, for this test case, we may assume to know the range of components that we may have, say from 9 to 144. And we may allow ourselves to know that the source is activating in just one random element or in just 2 random elements or something like that. So the idea could be that given initial guesses for our space, we may solve the reduced ordered model for entering global configurations. We can mark components where a suitable error metric is large, and then we can solve the full model in the marked components based on boundary condition coming from the other components, and then refine the local reduced order model. Okay. You see, if you're familiar with the mesh adaptation, that this is a standard mark the refine paradigm, okay, but applied in the context of component-based model reduction. So here's some results. So on the left, you see performance for, let's say, the smooth sampling with alpha equal to 1, so the best sampling that we had. And on the right-hand side, the Gaussian sampling. And you see that before starting these adaptive enrichment iterations, let's say these approaches is much, much worse. Okay. But then when we apply this adaptive enrichment technique, after 3 iterations, we get performance which is comparable to the performance that we obtained using the better sampling technique. Okay. So let me just draw some conclusions. So I believe that component-based model reduction offers the opportunity to address large-scale parameterized problems because it can deal with topology changes, high-dimensional parameterization. And of course, the 2 main questions that we need to address, the effective implementation of, so basically are the reduced formulation. So how can you glue together local ROMs to estimate the global solution? And how can we build good approximation spaces for each archetype component? In this talk, I presented 2, let's say, solutions, which one is optimization-based procedures, and the second one is related to randomized sampling plus enrichment. Okay. So I just as disclaimer, I don't want to pretend that that I invented optimization-based methods. That's actually very far from the truth. The optimization-based methods have a long history in domain decomposition, and here I mention a few works, and I'm happy to discuss more about that. What I claim here is that optimization-based coupling offers a valuable framework for model reduction because it reads as a minimal residual formulation of an interface problem. And we know that minimal residual is a well understood projection technique in model reduction. It does not involve compatibility conditions at interfaces, which may be very, very tough to enforce in the more in the model reduction framework. It allows for reasonably simple hyperreduction, and I can comment on that, and also enables rapid convergences combined with GNM. And here, again, the prerequisite is port reduction, really, rather than model reduction as well. So in terms of long-term goal, I think it will be pretty nice, and I want to mention that a few weeks ago, some people in the audience were there. There was this talk by Irina that I really liked. That Irina Tezzauri, she's working on that right now, on try to do hybrid modeling through model reduction. So try to combine different sources of information, rather, let's say, projection-based ROMs, full order models, data-driven approaches, all together in a unified framework, and try to be able to define a framework that also switch between the different approaches. What I hope that I was able to convince with this talk is that optimization-based coupling techniques can provide the natural framework to combine these such heterogeneous sources of information in a robust manner. On the other hand, I also try to justify the message that localized training still remains an outstanding challenge for model reduction. To my knowledge, randomized techniques have been extremely effective to identify low-rank structures for linear problems, first in the linear algebra literature, and then also in the model reduction literature. On the other hand, for nonlinear problems, there's still much to be done, and especially, as I already mentioned, as I mentioned in this in the particular example that I consider. On the positive side, I believe that adaptive enrichment based on an error indicator may alleviate the issue of sampling a little bit. In terms of perspective, I think here there's a lot of room for analysis, and in particular analysis of performance based on random sampling for nonlinear maps. I think this is a very cool topic, and from an analysis standpoint, and there are some results on that that I'm happy to share if for those of you that are interested in that. And another point is adaptive sampling. And as you all know, there's been a lot of theory on and a lot of interest on importance sampling variance reduction techniques for, let's say, Monte Carlo type estimates to estimate the mean of a certain flow, a certain quantity. There's still not much importance sampling techniques directly specified for data compression. And I do believe that this is a very important subject, and there's a lot to be understood on that. And with that being said, thank you for the attention.
Thank you very much, Tommaso, for the presentation. We have a few minutes for questions from the audience. So if you have a question, just feel free to unmute yourself. Maybe Mejdi maybe has a question. I
have maybe I don't know how to qualify my question, but do you think it's possible to conduct at least for the first part of the talk something around domain decomposition without overlapping, but by introducing the control of the flux as well?
Yeah. So yeah, I should have mentioned that. So basically, there are some works on that. I think one of the works is by Matzonsburger, and also, yeah, I think this work, basically, the way in which I did was like having essentially virtual, they call it virtual control on the flux, and then basically try to do the same analysis. So the short answer to your question is yes. One can also try to use, instead of the flux, the solution itself. So I have like the port, the solution really, and then kind of minimize the misfit in the flux, in the normal flux. This is also possible, and I think this is kind of related to hybridized discontinuous Galerkin methods. Yeah. Really. But yeah, the short answer is yes.
And still for the first part, do you have some mathematical result concerning the convergence with respect to the delta and maybe also?
So we have, so let me just one sec. So we do have some analysis for coercive problems.
It's good.
Which, you know, it's, I think, at least with standard arguments, I think it's the best that we can achieve, because I don't think, so basically, let's put this way. So if overlapping Schwarz converges, so whenever we can prove convergence for the standard overlapping Schwarz, we should be able to prove convergence also for OS2. But of course, the question is, when overlapping Schwarz does not converge, does this approach converge? Yeah. And that's, you can build some counterexamples in which basically for Helmholtz, for instance, in which you can prove that overlapping Schwarz does not converge, but this approach as unique solution, but they're quite artificial in a sense. So yeah. The question is, what can we prove for really non-coercive problems? But this, I think, is a very, very tough question.
Okay, yes. And especially I'm impressed by the fact that the convergence does not depend on the length of delta.
Yeah, so it seems like, so I think there's two things that are going on here. So I believe, so there are two things. So first of all, maybe, I mean, if you decrease delta, eventually it's going to break. So on this, I mean, I do expect that you still have this issue. But I think it's also related to, let's say, the characteristic length scales of your reduced order basis, the reduced order basis that you consider, in a sense. Because, I mean, you need some, I believe there is some kind of observability type of requirement that, of course, it becomes much tougher to realize whenever whenever delta becomes small. But still, I think, yeah, it's significant. So the empirical evidence is that GNM is significantly more robust than standard overlapping sparse.
En tout cas, thank you very much for this super travail. Merci.
Merci.
So Masa has a question. Please, Masa, go ahead.
Hi, Tommaso. Really enjoyed your talk. I might have missed this, but I think you talked about hyper reduction of not just the port bubble map, but also the objective function itself that you're optimizing. Could you elaborate a little bit on exactly how you're finding the sparse quadrature?
Yeah, so okay. So I mean, the short answer is that we use some point-wise empirical quadrature. That's the short answer. And in order to do that, so I should be able to know it, but so basically we assemble the let's say the global system for certain configurations, and once you've done that, we can like assemble the metric G and B that you need to plug in the non-negatively square formulation. And one comment that I have on that, which is quite technical, but I mean, you asked me. So there is a major difference. So one other approach here could be like to do, say, partition of unity. That's what I use in the second part. Okay. My experience is that for the second approach is much, much tougher to do hyperreduction because you have a strong coupling between components. On the other hand, in the OS2 formulation, essentially with some tedious but let's say straightforward rearrangement of the terms, everything boils down to something that is on the archetype component level. And so it is doable and you can use standard techniques.
Okay.
So
but you do consider a number of different, I guess, pairings of, I guess, the components. Yeah. I guess okay, all right, makes sense. All right, thank you.
Yeah, I think you have to do it. You have some kind of a randomized training of in also to do the hyper reduction.
Thank you.
Yeah, thanks.
Thanks, Masa. Ryan has a question.
Yes, very nice, Tommaso. Thank you. This was I really enjoyed the talk. And I have a couple of questions, but so just maybe more clarification. So, I mean, what you presented, if I understood correctly, is for the, so component-based model reduction. And since you mentioned this, I mean, in the spirit of what Irina presented in Bordeaux, so could you actually do similar things to put together, full order models or, other types of models? With this approach, could this be expanded to those cases?
Okay, so the short answer is, my claim is yes, absolutely yes, but I haven't done it. We haven't done it yet. Okay. But let's say, in the end of the day, I mean, Irina and also others have already done some kind of overlapping sparse with different methods. So one thing that we did was try to push the method to the limit in which you have, let's say, one reduced order model which was very under-resolved, and one was crazy resolved, like 2 modes on one side and 30 on the other side, something like that, because it was easier to implement and it did not. And in that sense, it turns out that the approach was quite robust to that. And this gives us hope that those kind of optimization-based couplings can be quite powerful. The other message is that I think, there's been theory on, I mean, sorry, not theory and practice on domain decomposition for like 30 to 40 years, I think. I'm not claiming that we are inventing a new domain decomposition methods, because that would be like silly, I think. But what I claim is that there's a little bit of difference here, because when you do the standard domain decomposition, you still have a lot of degrees of freedom on the ports. And this approach based on Gauss-Newton does not really seem to, you know, it requires that the number of degrees of freedom on ports is small. But if that assumption is satisfied, I believe that those, I mean, you can buy a lot from it. So it can be very robust to the kind of heterogeneous modeling. It can be, so I think that if you're willing to pay the price of do port reduction up front, I think we can succeed with hybrid modeling as well. Gotcha. That's kind of the claim, but that's more like, you know, a claim and proof.
Okay, thank you. And I have one short question, hopefully. So what you presented was for generic PDE, you know, I was wondering if you have something more specific. So if you have some convection as opposed to diffusion or different types of operators, would these framework change in any way or not really?
So the short answer is that the operator, the framework does not change. The question is how successful can be. Yeah. And so I think it's a very tough sell. So my personal opinion is that, you know, whenever you have structures that propagate, the issue of localized training becomes very, very tough.
Right, okay.
So that's I mean, the first bottleneck. I do believe that adaptive, so the kind of adaptive enrichment can help. I mean, but it's something that can help. So to push the limit a little bit larger, but it's still, I think the localized training is that for the OS2, I mean, overlapping sparse has been applied to a lot of problems. Again, convergence, to my knowledge, it depends on how much advection you have. That's my knowledge. This approach should be a little bit more robust, but still, I mean, we are not fundamentally changing overlapping sparse.
Great. Thank you.
Thanks.
Thanks. Are there further questions from the audience? Okay, if not, maybe I'll ask my final question then. For the second part of the talk, you mentioned a couple of times, and I think it was also mentioned in the very last slide, that nonlinearity is a challenge when dealing with the sampling, basically. And I would suggest that, I mean, I definitely agree that nonlinearity, having a nonlinear problem is a challenge, but maybe there are also linear problems which are still challenging on their own. For instance, if I think of fluid dynamics, and if I think of a Stokes problem, there is definitely a challenge in choosing the boundary conditions at the interfaces, because there is a constraint of mass conservation. So you couldn't just go and throw in whatever random boundary condition you want, because that would violate the physics. So my question is, has there been any progress recently in this direction, and what would be say reasonable ways of tackling that, for instance, based on the sampling that you propose for the boundary conditions?
So thanks for the point. I mean, I was probably a little bit, let's say, it's certainly true that nonlinear increases a lot the difficulty. The example that you make, I think you raise a very good point, but I think that can be solved. So let's put it this way. So it's all about, so the idea that you can just throw a Gaussian random variable in each point of your, let's say, of your boundary, and then expect that you're going to find a good reduced space, I think it's very optimistic, and it can dramatically fail. It's certainly going to fail for nonlinear PDEs, but I'm inclined to say that also in the linear case can fail. So there are certain requirements that you can impose. For instance, mass conservation, I think it's something that you need to ensure somehow. If it boils down to a linear type of constraint, say that, I don't know, some kind of linear constraint, I think that's something that is still doable quite easily. Because still you have to remember that the number of degrees of freedom on the port is not going to be huge. So you can do things like SVD or, to compute the null space of some matrix, So in that sense, I do believe that this can be, let's say, addressed. Of course, nonlinearity is tougher because it becomes a nonlinear type of constraint. And that's, even if the number of degrees of freedom is not enormous, still it can be pretty tough. But yeah, I think that sampling is a pretty tough problem in itself. Yeah.
Okay. Thank you very much, Tommaso. Let's see if there are further questions from the audience. If not, I would like to thank Tommaso again for his presentation. And we'll see you next Tuesday. Bye.
Thank you very much.